Let's do a few more problems where we're figuring out the additive constant and the antiderivative. We can't always do that, but sometimes when we're given some kind of information about what point that antiderivative has to go through, that's when we can figure out the additive constant. Let's take a simple problem like this. Little f equals 5, just a constant value. What is big F? What is the antiderivative of little f? Well, you could say it's the integral of 5 dx. Integral of 5 is 5 times x plus c. And then let's suppose we also know that a particular spot on big F, that big F of 3 is equal to 9. So what can we do with this? We can say big F of 3 is 5 times 3 plus c, which is equal to 9. So this 3 is going there, and the 9 is going there. So that's what c equals 9 minus 15, which is negative 6. So then we can say big F of x is 5x plus negative 6. So can we say that the value we're given, like the 9 here, is just the c value? Well, no, that's not what we ended up with. So we can't say that the given value is just c, even though that's how it ended up working out in the position, velocity, acceleration problem in the other video. Let's diagram again kind of what happened. We had our function f, which was just a constant at 5. And then we had our general f prime, general big F is 5x plus c, which is a sloped line. Could go through the origin, could be any of those lines. And then we said we know a particular point is at 3, 9. So our particular f was out here at 3 and went through 9, and this line has the same slope. It's kind of just one of those slanted lines. So the value we're given for c is not always, the value we're given for the function is not always the value that c will end up being. Let's do another one. Let's say f of x, little f of x equals negative sine x. What would you say big F of x is? It would be the integral of negative sine x dx, which is, what's the integral of negative sine? What gives negative sine when you take its derivative? That would be cosine x plus c. Now that plus c is not added to x before you take the cosine. Let's say that we also know that f of 0 is 4. So we would say f of 0 is cosine of 0 plus c, which is equal to 4. What is cosine of 0? It's really tempting to say it's 0, but it's 1. So 1 plus c equals 4. So c equals 4 minus 1, which is 3. So we can say f of x equals cosine x plus 3. Did the 4 we were given is the y-intercept, right? If x equals 0, y equals 4. But is c the y-intercept here? No, the y-intercept is 4, but c is 3. So we can say c isn't always the y-intercept. So let's diagram again what happened. We had f of x was a negative sine wave. and then we took the antiderivative and got cosine, but it's cosine that could be shifted up or down. So it could be a regular cosine like that. It could have been slightly higher. It could have been even higher than that. It could have been lower. It could have been lower. So this is our general f, and then our particular f, big F, is the one of those curves that goes through 4. So it was cosine plus 3, which means it's not to the same scale here, but it's one that starts high up above enough that it doesn't even come down and touch 0. Let's summarize what we did in Desmos as a graphical way of finding out C. So we said f of x equals whatever we were given, big F of x equals whatever our by-hand antiderivative was, blah, 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 plus C. And then we made C a slider. And we even had to increase its range sometimes. And then we put a point like 0, 4 in the problem we just did, or 3, 9 in the other problem. So that's a plotted point. And then we adjust the C slider until big F goes through that point. And you might even need to adjust the range of C so you can make C bigger.